So welcome back, everybody, and welcome to the last lecture. So the plan today is to actually discuss topics like Boltzmann machines and quantum Boltzmann machines. But since this is the last lecture and we are not that many today, we're just going to skip this topic and we move directly over to a summary of the course. So you can look up some of the slides here and on Boltzmann machines. And for those of you who have taken a course in advanced machine learning, you've also met the classical Boltzmann machines. And there are also some links with the connections to quantum neural networks. And for those of you who have studied many-body physics, there are actually many interesting links with many-body physics. What I would rather do then is to jump over to the summary and perspectives for future studies. And that means that we will basically just have one lecture today, and then we spend the rest of the time on project work, if that's okay with everybody. And for those of you interested in Boltzmann machines, we can have separate sessions if there is an interest in that. So the course philosophy and structure, we have essentially two parts, one on quantum computing, and the thing which I should do also, since I forgot to do that, is to put on the screen so you can see my slides. And so basically the two parts of the course contain then one part on quantum computing and the other one on quantum machine learning. And this is what has kept us busy from April and May. So I wanted to give you a kind of a bird's view on many of the topics which we have been dealing with in this semester, and actually quite many. So these two main parts, and one of the kind of central aspects of what we have done is to use variational methods, which are hybrids of a quantum computing applications of an algorithm on a quantum computer and a classical optimization part. And we've been looking at the VQE, which is a central algorithm, which is a part of this family of variational quantum algorithms, which lead to what we have defined as a parameterized quantum circuit in terms of some parameters which are optimized classically. But we have also looked at what we call fault-tolerant algorithms, like the quantum Fourier transformations. We have the quantum phase estimation algorithm and the HHL algorithm for calculating for solving linear algebra problems. So key themes which we have looked at is entanglement and measurement, the variational circuits for the noisy quantum computers, which we have presently. We have looked at fault-tolerant algorithms and quantum-enhanced machine learning. And we've also been solving ordinary differential equations with quantum methods. So like last week, we discussed the solution of the Poisson equation using quantum physics informed neural networks. So the first week was essentially us establishing the language. So we looked at 1-qubit systems, pure states versus mixed states, composite systems, and then some basic operator algebra on Hilbert spaces. And these are topics which many of you have encountered in previous courses. So that was basically the first week. The second week, and the third week, we looked at the tensor products and entanglement. We defined this important property of the density matrix. We looked at the entanglement, pure and mixed states. So the classical case is this Bell state, which you see displayed here. And when you trace out the density matrix for a subsystem, so this is actually the state which you see here under the bullet, under the box with the key concept entanglement. This is one of the classical Bell states where we have entangled 2 qubits. And this is a state which cannot be written as a product state. And when we trace out the density matrix for one of the subsystems and we calculate the entropy, we get a log 2. And the log, the von Neumann entropy simply just expresses the degree of surprise, in the sense that if you have something where you know exactly that this state is, the system is in that state, that is a well-defined system. There is no surprise. And then the von Neumann entropy is exactly equal to 0. And then the standard von Neumann entropy and also the classical information entropy, also called the Shannon entropy, is a quantity which is given by the probability times the log of the probability. And in that case, it expresses simply the degree of surprise. And we looked at reduced density matrices where we took the trace out of one of the systems. And what we saw then, if we take this Bell state, which you see in the box here, if you then trace out one of the subsystems, you cannot say whether the particle in the subsystem is in state 0 or state 1. But the state of the whole system is actually a state which is well defined. So we know that this is in a 0, 0 plus 1, 1. But then when we trace out the subsystem, we cannot define whether the qubit is in state 0 or state 1. And then we looked at entanglement measures. So this is actually a field which the studies of different types of entanglements and different entropies. So the measure of entanglement is something which we haven't discussed that much. We have just been using entanglement, and that is actually a course by itself. So the information content. And we do have a course in the Department of Mathematics, which is actually called Quantum Information Theory, where these topics are with density matrices, von Neumann entropies, different types of entropies are explored. So if you're interested, that's a course which often leads to more advanced mathematics, which we have stayed away from because we have been more looking at the implementations and the possibility to solve specific physical systems. So in the fourth week, we looked again at entanglement and entropies. We looked at separability criteria, and we also introduced gates. So we had all these kind of simple gates, simple qubit gates, 2 qubit gates. We discussed the gate universality, so that the gates which are listed here are typical universal gates, and you can actually define any operation on a quantum computer with these gates. And these are unitary gates. And we also started to look at very, very simple Hamiltonians. We had a 1 qubit Hamiltonian, and we had a 2 qubit Hamiltonian, which you had in project 1. And this was actually, in that week, that was the bridge towards the VQE, because the variational quantum eigensolver, because we actually looked at the solution of this Hamiltonian problems. That means finding in particular, the lowest energy of a given system in terms of gates. So actually, this way of expressing or solving physics problems, like finding the eigenvalues of a system with gates, is actually much more intuitive than the one you're used to when you think of a standard course in quantum mechanics, where you begin with the basic mathematics. Here, you're actually simulating a physical system with another physical system. And every gate is a physical operation, where you actually can rotate by, let's say, some applied laser or magnetic field, a physical system, and you perform operations on a physical system to solve a problem. So in a sense, this is kind of one of my hobby horses, because I've had students in this course who had no quantum mechanics before they took the course, but they felt that they got an intuitive understanding of quantum mechanics because you can illustrate every physical operation in terms of gates. So a gate is actually, when you think of it and you take it out of the context which we have been looking at, is a physical operation on a system. So these gates are actually things you can realize by manipulating systems of electrons or neutral atoms, superconducting qubits, etc., etc. And this is also a topic. The actual quantum hardware is something which we haven't discussed much in this course. We've been mainly focusing on the algorithms. So the quantum gates and simple algorithms is something which we then looked at. And we went through the VQE, where the thetas are the different rotation angles which appear from the application of different rotation gates, 1 qubit gates. And these 1 qubit gates, they are typically expressed in terms of these rotation angles along the X, Y, and Z axis, and they represent a state for each qubit on the Bloch sphere. And then we can do a product state. If we do a product state, we will never be able to catch correlations in the system. And that's why we have to bake in a 2-qubit gate, like a C0 gate. And then when we do that, we have a parameterized quantum circuit in terms of the angles theta, which are then optimized. So the quantum part, or the application on a quantum computer, is then given by the different rotation matrices and the C0 or swap gates. And then we have a classical part where we do the optimization. So we implement the VQE for simple 1 and 2 qubit Hamiltonians. That's in project 1. We did design the circuits, and then we evaluated the energy expectation, and then we had the classical optimization loop. So that was essentially what we did in project 1 in the very beginning. And that is a so-called parameterized quantum circuit. Then another central topic which we introduced is actually the parameter shift rule for gradients. And as long as you have everything in terms of Pauli X, Y, and Z and the identity matrix, you can actually get the analytical expressions for the gradients. And that means that you just have one circuit which you use repeatedly. So you calculate it for the Hamiltonian itself, for example, or if you do a quantum neural network, that will also be a parameterized circuit. So E then would actually be your quantum neural network. So the thing which is nice with this way of thinking is that you have basically the kind of same recipe. And you can use an adaptive VQE, which is also one of the alternatives of project 2. And then we have the shot noise and measurement strategies. And the shot noise is actually important because some people actually in project 1, they forgot that when they were actually dealing with the expectation values, you have to see them as a numerical experiment. And then we looked at the 1 qubit simple models, 2 qubit problems, and then we mapped the physics to qubits. And then we also started to introduce a Lipkin model, which was the final model which we implemented in project 1. And for those of you taking a course in many-body physics, you have already encountered the Lipkin model. So there is if you're taking a course in many-body physics, you've actually seen many different ways of solving a many-body problem. And I hope that's a kind of important message which many of you actually see. So the Lipkin model is a 2-qubit Hamiltonian. We had a full VQE pipeline for the Lipkin collective model. We benchmarked that against exact diagonalization. And then we also looked at ways to optimize, whether you should do a measurement on one of the qubits only or on all qubits. So in present days, quantum computers, you actually make a measurement on all the qubits. And in the follow-up week, we actually looked at the more general case where you can take a Hamiltonian from, let's say, quantum chemistry, where you have single particle orbitals. There you have different sets of single particle orbitals. Those of you doing quantum chemistry, you're probably familiar with that. All the different basis sets which are optimized for a specific problem. And then you could then transform your Hamiltonian by what we discussed as a Jordan-Wigner transformation. And one of the cases we looked at was actually a pairing model, which many of you have encountered in a course in many-body physics. And then there is in the Jupyter notebooks, there is an example on where you actually solve the many-body problem for the pairing model instead of the Lipkin model. So the whole idea is that you transform a Hamiltonian in terms of Pauli X, Y, and Z gates and the identity gates. And essentially what you ended up with in project 1 was to have a variational quantum eigensolver, which is able then, with modifications, to solve different many-body problems, like a pairing Hamiltonian or more advanced ones. So one thing which we also had as a follow-up for project number 2 was to, for instance, use Qiskit and run the same system on a quantum actual quantum computer like IBM's computers. And the Qiskit is actually coupled up with a library which is called PySCF, which contains essentially everything you want to know about quantum chemistry algorithm, copper cluster theory, time-dependent DFT, density functional theory, time-dependent Hartree-Fock, multi-configuration, time-dependent Hartree-Fock, FCI, etc., etc. And that's linked with the Qiskit so that you can actually then take a given Hamiltonian, like the one which is relevant for the H2 molecule, and you can solve that one on a quantum computer. So you can simulate realistic systems. So these are just the perspectives beyond what we have been doing. And at the end of the slides here, you will see some perspectives for future studies. So that was essentially the first part. Then what we did was to actually move on to algorithms which do not depend on this mix between classical and quantum. So these are so-called fault-tolerant algorithms, which can be applied on a real quantum computer, but you need error correction codes. So the error correction part is something which we have not discussed. This is a course by itself. So there are many topics here which there is no way we can cover everything into this course, actually. We would have needed double as many lectures per week. And the quantum Fourier transform is actually the basic kitchen ingredient, which is then used in many of these algorithms. And one of these is actually the quantum phase estimation algorithm for finding the eigenvalues of a system, which is also used in the HHL algorithm. So for the quantum Fourier transform, we actually developed codes which then perform these. And we also compare that with the speed up and the exponential speed up which you get over classical fast Fourier transform. So we looked at the different ingredients and also the circuit decomposition, which gives a huge advantage compared to even the classical fast Fourier transform. When we had that in place, we with the quantum phase estimation, we can estimate the eigenvalues of the unitary transformation. We put up the way we construct the circuits and the precision of the calculations, and we looked also at applications to the specific Hamiltonians in order to find the eigenvalues. So the pairing model is one of the models which you will find, and also the Lipkin model in the Jupyter notebook for that specific weeks, 10 and 11. And in week 11, we went over to the HHL algorithm for solving linear systems, where you also need the QPE as a subfunction. So the essentially what we have then is a machinery where the QPE uses the quantum Fourier transform. And with the quantum Fourier transform, you find the eigenvalues with the QPE. And this can be baked into the HHL algorithm for solving linear systems. This is also interesting for many body physics, because for many body problems, like if you're dealing with Green's function theory, the Green's function is actually the inverse of the Hamiltonian, or the resultant, the Hamiltonian minus the energy of the state. And we looked at the exponential speed up, limitations and implementations and codes. So that was the HHL algorithm, which we had in the 11th week. Then in week 12, we actually continued with the HHL and looked more at codes, and we had a deep dive into the algorithm. We looked at the full implementation, the calculations on why we had the ancilla qubit, the eigenvalue inversion, the amplitude encoding of the vector B, which is known, and then a little bit about error analysis and success probabilities. So with these algorithms, which are more the so-called fault-tolerant algorithms, we then turned into what we might call just the NISQ-era quantum machine learning methods. So the HHL has also been used in machine learning. And the reason for why it has been used in machine learning is that in machine learning, if you think of linear regression, this is the same problem you would actually solve in a linear regression case. You have to invert a matrix. So people have actually applied the HHL algorithm to machine learning problems, which means that then you could run a machine learning problem without invoking a classical algorithm. However, the depth of the circuits become pretty deep, which means that error corrections are actually needed. So that's a topic which we haven't discussed. Then we had the quantum approximate optimization algorithm, QAOA, which is an example of a parameterized quantum circuit, which serves as a kind of gateway into quantum machine learning. So it's actually a quantum optimization problem. It's a machine learning problem, but with a fixed Hamiltonian. So, and that fixed the type of problem which you're dealing with is a kind of binary optimization problem. But it is in itself a quantum optimization problem, which is a kind of prelude to what we did later with quantum machine learning. And that was 4 weeks ago, actually, when we went through that. And in the lecture notes, there are codes, etc., which you can also look up and see how we can implement it. And there is an implementation actually on financial data. So the QAOA algorithm is a very popular algorithm for applications of quantum machine learning algorithms to finance. So it's the optimization part of VQE, and it actually serves as a kind of gateway to quantum machine learning methods. So then we went into, actually there's one thing which I was a little bit hesitant to discuss, which is a kind of intermediate step, which is called quantum support vector machines. I skipped it this semester because the support vector machines is a very popular machine learning method, but it's just actually based on plain linear algebra. And I skipped it because I never gotten very excited by the method. But it's a very useful intermediate step if you dive into quantum neural networks. So I will actually put it in the final lecture notes. But what we looked at was the data encoding strategies, which is important because the data can be classical or we can have quantum data. And if we have classical data, we need to encode them for a quantum computer. So there were different strategies like the amplitude encoding, angles, etc., etc. And then we end up with a parameterized quantum circuit, and the expressibility and the entanglement becomes important. So you can again see this as a numerical experiment where you have a quantum circuit with parameters. After you have encoded the data, so first you encode the data, you initialize typically the system with all qubits in qubit 0, and you take the tensor product of this. This is your initial state. And then you transform this so that you can encode the data. And then when you've done that, you have a standard parameterized quantum circuit where you optimize the parameters like we did with the VQE. And we discussed the different variational circuits. So in that week, we also had some programs where we have a classification problem and also standard linear regression problem. And then we also looked at the connections to the QAOA algorithm. And there's also links to classical deep learning. So I'm just going through what we've done in a way week for week so that you get if you look at these slides, you have a view of what we have covered. And at the end, you will see links to some future perspectives. So we also looked at last week and the week before. We actually looked at the implementation of quantum physics neural networks. And we looked at the solution of an equation which we have encountered before. I mean, the Poisson equation, which is in one dimension, which is a 2-point boundary value problem. We looked also at the solution of the heat equation, and we found that the pins actually lead to much less parameters than you would have if you were to deal with a classical neural network. We can also use topics like automatic differentiation on circuits because we have an analytical expression for the gradients. So we solved ordinary differential equations and PDEs, boundary conditions, and how we encode them. We looked at the gradient computation via the parameter shift rule. and also we discuss codes there. So this is actually the marry the physics in informal training paradigm with the expressive power quantum circuits. Now, I should say that there's a lot of ongoing research now on the quantum advantage of quantum machine learning algorithms. And there is no definite answer yet. So this is just an open research area. But clearly, if you can get away with much less parameters than when you deal with a classical neural network, then clearly this becomes a very, very interesting alternative to standard machine learning algorithms. Then what we have, and this was actually the topic I thought of doing today, but since it's the last lecture, I just leave this as a self-study material. So I will not discuss quantum Boltzmann machines, also because I would actually have had to cover classical Boltzmann machines, and some of you have studied them in Physics 5429, which is a course on advanced machine learning. And there we cover actually in depth the classical restricted Boltzmann machines. So take a look at the slides. But this is actually an interesting topic because in quantum Boltzmann machines, you can actually illustrate how statistical mechanics and machine learning actually merge together. This is actually a very active research topic. And so what we have is we have links to VQE and variational circuits. We have, so this is a red thread throughout the course. I mean, and a theme which pervades this course, parameterized or variational quantum circuits. And the thing which we haven't discussed much is actually generative quantum models and generative methods, because a Boltzmann machine, what you end up doing is that you train a probability distribution. So classically, a Boltzmann distribution is obviously something which everybody's familiar with. But what you would do is to replace that one with a quantum Boltzmann distribution. And then the partition function is actually the trace of the exponential which you have in the standard Boltzmann distribution. Okay, so the thing I wanted to say a little bit about, so this is just a quick summary. So the kind of overarching goal is actually to equip you guys with the theoretical foundations and practical implementations to design, analyze, and run quantum algorithms in near-term and fault-tolerant hardware. This has been the kind of overarching goal. So when you now look at the semester, think of this last box here, the statement there, and whether this is something which you recognize as what we've been doing during the semester. So this is a kind of overarching goal so that you have an understanding of the standard quantum algorithms on both near-term and fault-tolerant hardware. So you could say that the course is expressed basically in that statement there. So this is roughly what we have done during the semester. And then some perspectives. So these are things which also move into the second project, and some of you are actually looking at that. I know that there are people who are actually looking at the unitary copper cluster and the adaptive VQE. Quantum error mitigation, there's also somebody's doing that in the second project. One could also look at benchmarks where these NISQ devices outperform classical methods. And there are actual examples of that, like there are implementations of the QAOA algorithm, which outperform classical methods. One of the problems is obviously the study of barren plateaus, which means that the training of in the gradient optimization reaches an area where basically there is no change in the gradients. And then typically the training can stop before it should stop. We have fault-tolerant algorithms. There's actually a lot of interesting stuff going on. There is something which is called a quantum linear algebra, quantum support vector machine, and quantum PZA. There's also quantum walks and search algorithms, Grover speedups, etc., etc. This is on fault-tolerant algorithms. Lots of applications in quantum chemistry and also in nuclear physics and condensed matter physics. So there are many, many fields in science now where these methods are being used. So in quantum chemistry, electronic structure, I mean the VQE, the unitary copper cluster, has actually been a method which has been applied over the last 10 years. So there is a lot of literature on quantum chemistry applications of the VQE. So the quantum advantage, fault-tolerant simulations of strongly correlated systems, imaginary time evolution, thermal states is actually very important for quantum Boltzmann machines, for instance, and finer temperature properties on quantum hardware. In high energy physics, people are actually looking at lattice gauge theory to simulate quantum electrodynamics, quantum chromodynamics. Also, the Hubbard model is one of these famous spin-like type of models. We have quantum gravity. Quantum sensing is a very hot topic. And so if somebody's interested in that, there's a big experimental activity at the University of Oslo, at the Center for Material Science, where quantum sensing, both theoretically and experimentally, is something which is studied. We have, if you think of quantum hardware or quantum machine learning frontiers, we have quantum generative adversarial networks, quantum diffusion method, and also quantum Boltzmann machines. There is quantum reinforcement learning, which is a hot topic. There are no clear, still yet, solid proofs of quantum advantage, but it's actually an active research field. We have classical quantum hybrid. We also have on hardware and open challenges, qubit platforms, which are being studied. Error correction is a very hot topic, which we have not covered at all. And clearly, how many logical qubits for quantum advantage on real-world problems. So quantum advantage requires both better algorithms and better hardware in tandem. So these are actually very active research fields. So this was roughly a kind of perspectives on future work and possibilities. So one of the topics which is pretty hot nowadays is actually the quantum error correction part, which is getting better and better on fault-tolerant machines. So the kind of a mix of both better algorithms and better hardware in tandem is something which we are going to see much more of in the coming years. And by 2030, for instance, many of the companies which develop quantum computers like Fujitsu, IBM, etc., they are promising to have something like quantum computers with 1,000 logical qubits. So nowadays, most of the computers you can access give you something between 20 plus logical qubits you can do operations with. And some of the quantum machine learning algorithms, like a quantum neural network classification, has been typically been applied mainly to toy models. So you need actually to ramp it up to many more qubits before these methods become competitive compared with the classical ones. But I hope you see both the excitement of what is coming and also have a deeper understanding of the algorithm, and that we're actually simulating physics problems on a physical system. So we are manipulating a physical system to simulate or solve a problem. And this can be a linear algebra problem, like the HHL algorithm, or it can be us wanting to get the eigenvalue of a physical system. And then we use another physical system to simulate that. I think that's pretty cool. And that was originally Feynman's idea when Feynman presented his basic ideas of a quantum computer, to simulate a set of equations using a physical system. In a sense, when you solve your problems on your laptop, you're using a physical system. Your laptop is a physical system. But you don't manipulate physical states in it in the way you manipulate a physical state in a quantum computer. Okay, so we skipped the stuff with Boltzmann machines, and this is essentially the last slide of this semester. And I would like to suggest that we spend the rest of the time discussing the project and where you are, and try to see if we can get a kind of handle on problems, etc., etc. So, thanks for the attention, guys.